Materials. Materials are all around us. We use them in our everyday life. But what are the most common materials? What do they make? And what properties do they hold? These are the key insights that we will try to uncover in this module. For engineering purposes, materials can be divided into 4 key areas. The first is metals. Metals are the widest used of the 4 materials. Even if a material is not made of metal, metal will have been used at some point during its manufacture. Metals are used for everyday objects like cars, buildings, and bridges, but also go into extreme applications like jet engines, mining equipment, and space exploration. Even the tallest buildings in the world are only possible due to metals. The second material is polymers, which includes plastics. Polymers are widely used in many different industries. Natural polymers consist of amber, wool, silk, natural rubber, and cellulose, which is the main constituent of wood and paper. These natural polymers have been used for centuries. More recently, synthetic polymers have been produced, and these have revolutionized modern society. These include synthetic rubber, nylon, PVC, polystyrene, silicon, and many more. The third is ceramics. Ceramics have been used for thousands of years, and the most common two are glass and clay. Clay was the first material that we learned to transform into another state using fire. This was done about 29,000 years ago, when clay was formed into decorative figures. Much later, clay was used to form items like jugs and bowls. Glass, which is mainly made from sand, was mastered by the Romans, who unlocked the secret of blown glass by mixing it with minerals. The Romans were the first people to use glass for windows. The fourth material is composites. A composite is a combination of 2 or more materials. Composites have been used for centuries in the form of concrete. Again, it was the Romans who really mastered the process. In text from 25 BC, different aggregates are discussed for use in lime mortars. In 1853, steel bars were first added to concrete, making it one of the widest used composites, reinforced concrete. Metals can be divided into 2 subgroups, ferrous and non-ferrous. In ferrous metals, the main constituent is iron, and this group consists of steels and cast irons. For the amount of strength that is achievable in steel and cast irons, it is a cheap material. This is because iron is one of the most plentiful elements in the Earth's crust. Non-ferrous metals include any other metals. Some examples are aluminium, copper, zinc, titanium, and nickel. Metals have good electrical and thermal conductive properties. They are ductile, strong, tough, and have strength at temperature. Polymers are organic carbon-containing molecular chains. They have a wonderful array of properties and are primarily made up from hydrocarbons. These are the building blocks of plastic. Hydrocarbons are a byproduct from petroleum industry, and due to this, they are abundant and therefore a cheap material. The carbon and hydrogen which make up the plastics are the key to how they work, because they can form together to produce long chains. This enables plastics to be versatile and easily processed. How the material is processed can produce the desired combination of properties. The strength can be varied, the toughness can be varied, they can be a good conductor of electricity and are often very good insulators. Again, ceramics can have a wide array of properties, and in recent years we have really begun to understand them. Semiconductors have been produced which, when cooled, have virtually 100% efficiency in electrical conductivity. To put this into perspective, current electricity cables lose about 5% of electricity through resistance. With the loss in the world's electrical energy for 1 year, you would be able to power over 3 million washing machines constantly for 100 years, meaning that each person on the earth could run a washing machine constantly for 15 days for free. Ceramics are an inorganic, non-metallic material. They are chemically bonded and can have a structure that is crystalline, non-crystalline, or a mixture of both. Ceramics are known for their lightweight, high strength, high hardness, good heat and wear resistance, making them excellent for furnace linings, although ceramics can be brittle. Composites consist of a matrix or binder and a reinforcement. Composites affect our everyday life, probably without our awareness. Concrete is likely to be the most common composite and has shaped the modern world we live in. Concrete consists of a cement matrix and a stone or aggregate reinforcement. Another is fiberglass, with a matrix of plastic and a reinforcement of fine strands of glass. In the 1960s, scientists set out to make plastics as strong as metals. Through their research, they produced carbon fiber. This is also known as carbon fiber composite, and it is made from fibers of carbon and plastic, similar to glass fiber. This gives unique properties of strength, stiffness while being lightweight, but carbon fiber is very expensive. Only over the past 60 years have we really understood metals on an atomic scale. In metals, atoms are arranged in an orderly manner, giving them a crystalline structure. Metals consist of two common arrangements of atoms, one with an atom at each corner of a cube and one atom at the center. This is called body-centered cubic. The other has an atom at each corner of a cube and one atom on each face of the cube. This is called face-centered cubic. Mild steel arranged in a crystalline manner should have a strength of approximately 20,000 megapascals, which is equivalent to supporting the weight of an elephant on a 1 mm thick piece of wire. But mild steel has a strength much lower than this. It has a strength of approximately 1,000 megapascals, or a strength 20 times lower, which is equivalent to supporting the weight of a sheep from a 1 mm thick piece of wire. The reason that steel is reduced in strength is due to the imperfections in the atomic structure. These are called dislocations. Normally, when we think of crystals, we imagine that we can smash them under a load like a hammer, but the interesting thing about metals is that when pressure is applied, the atoms can move, and this is how they can be formed and worked into different shapes. The dislocations help this deformation process. In metal, the atoms are arranged in groups. These groups are called grains. These are evident when you look at a zinc-coated surface, or what is known in the industry as a galvanized surface. These grains can work both in favor and against the steel. They can increase the ductility of the steel, but where the grains join, the grain boundaries, are areas where impurities collect. Metals can be strengthened by adding more than one metal together, such as copper and tin, to make bronze. In this example, the two combined has far greater strength than each of the individual metals. The sum is greater than the parts. We can also change the properties of metals by adding non-metallic elements, like carbon. If we take steel, there are hundreds of steels, all with slightly different properties, some tough, some strong, other resistant to rust. These steels are produced by the same principle as bronze. We take one element, iron, which is the bulk of all steels, and add another chemical element, often called alloying elements, to it. To name a few, we could add carbon, manganese, nickel, copper, molybdenum, boron, chromium, niobium, titanium, and vanadium. In this way, we can tailor a steel to a specific application. So, we take our grains of iron atoms and our alloying additions, which often have a different atomic size. For example, carbon is small, nickel is slightly smaller than iron, and molybdenum is slightly larger than iron, and add them together and we get a distorted structure. When we add atoms that distort the atomic structure, this makes it more difficult for the atoms to move around and makes the material stronger. Depending on the type and amount, we can make a metal much stronger. The smallest elements, like carbon, lay in between the iron atoms. These are called interstitial. We have the largest atoms which replace an iron atom, like molybdenum. This is called substitutional. This type expands the structure. Or we can have smaller substitutional atoms, like nickel, that collapse the structure. So, in summary, engineer materials can be divided into 4 key areas: metals, polymers, ceramics, and composites. Composites are as high-tech as carbon fiber and as abundant as concrete. Composites are a combination of two or more materials. Composites consist of a binder and a reinforcement. Ceramics were the first material that we learned to transform from one state to another. Ceramics are inorganic, non-metallic materials. We have really begun to understand ceramics in recent years with semiconductors. Polymers have revolutionized modern society. Plastics are made from hydrocarbons, which are a byproduct of the petroleum industry. This makes them abundant and cheap. How the polymer is processed has a large influence over its properties. Metals are the widest used of the four materials. Metals are divided into two subgroups: ferrous, containing iron, and non-ferrous, not containing iron. Iron is one of the most plentiful elements in the Earth's crust. This is used to make steel and cast iron, which makes them efficient in terms of cost per the amount of strength achievable. The atoms in metals are arranged in an orderly manner. They have a crystalline structure. The theoretical strength of metals is much higher than reality due to dislocations. The crystals of metals are arranged in grains. The properties of metals can be manipulated by adding other chemical elements to them. These elements distort the atomic structure, making it more difficult for atoms to move around.